My project studies the effect of river water and seawater on arsenic absorption to goethite and ferrihydrite. We are studying this because global sea levels are rising due to climate change and causing increases in salinity along the coasts. Predicted flooding is a risk to coastal contaminated soils because sequestered contaminants may be mobilized during reductive dissolution of iron oxide minerals. These minerals have a very high affinity for toxic elements such as arsenic. Mobilization of arsenic is detrimental to the environment as well as public health due to its carcinogenic nature. Because it is still unclear how arsenic-sorbed iron oxides will behave in the face of sea level rise, we have studied the effect of salinity and pH on arsenic absorption to goethite and ferrihydrite. So to study this, we have conducted both sorption isotherms and pH envelopes in artificial river water and artificial seawater, which we have made in the lab. All experiments had a solution density of 2 grams per liter of either goethite or ferrihydrite. For the isotherms, we used an arsenic range from 0 to 2 millimolar and kept them stable at pH 6 for 24 hours. For the pH envelopes, we used a pH range of 3 to 9, which were also equilibrated for 24 hours. The initial arsenic concentration in these was 1.67 millimolar. Upon completion of the 24 hours, all slurries were centrifuged, filtered, and analyzed via ICP-MS for total arsenic concentration. So going over to the results of the isotherms, in Figure 2, we can see the absorption isotherm for arsenic onto goethite. The x-axis shows arsenic equilibrium concentration in millimole per liter, and the y-axis shows mole absorbed arsenic per kilogram goethite. The green line represents artificial seawater data, and the blue line, river water. We can visually see that more arsenic was observed to goethite in the seawater. If you look at Table 2, this difference is reflected in the differences in Kf and N values that were found using Freundlich parameters. Looking at Figure 3, the x and y axis remain the same, except we are looking at absorption onto ferrihydrite now. We can see that the two curves are the same, overlap each other, indicating that there is not much difference in arsenic absorption based on seawater and river water in this mineral. This is once again reflected in the Freundlich parameters, as they are both similar for both water types in ferrihydrite. This is most likely due to the large surface area of ferrihydrite, and us not reaching the absorption maximum of the mineral. As we move on to Figure 4, we can see arsenic absorption onto goethite as a function of pH. Green is once again seawater, and blue line is once again river water. The x-axis shows pH, and the y-axis is absorbed arsenic. Throughout the pH range for goethite, more arsenic is absorbed in the seawater. In Figure 5, we can see that arsenic absorption of ferrihydrite as a function of pH. Here there is not much difference in arsenic absorption until about pH 8. At this point in both graphs, we see that in the river water system, significantly less arsenic is absorbed than in the seawater system. This can be accounted to the point of zero charge of these minerals, which is around 8. At this point, the surface of the minerals begins to become negatively charged, which leads to less arsenic absorption. In the seawater, however, this effect can be counteracted by cations such as magnesium and calcium in the solution. They absorb onto the mineral surface and alleviate the negative surface charge, thus promoting more arsenic absorption in the seawater. In order to further investigate arsenic mobilization due to sea level rise, future experiments need to be conducted. So, as you can see in the future work section, we would like to expand the range of arsenic concentrations in the ferrihydrite isotherms in order to hit the absorption maximum of the mineral. We hope that this can tell us more about the differences of arsenic absorption in seawater compared to river water for this mineral. In addition, to study the effect of arsenic absorption on the point of zero charge of the minerals, we will be looking at the zeta potential after arsenic absorption. We hope that this work can help improve the current understanding of redox-sensitive arsenic mobility and help contribute to remediation plans as our community continues to anticipate the effects of sea level rise on our coastal soils.